Hello and welcome back to Year 9 Chemistry. This is Week 8, Session 1, the Group 0 Noble Gases and Comparing Group Trends. We've met the dramatic alkali metals and the fierce halogens. Today we meet the calm, quiet aristocrats of the periodic table, the noble gases. They barely react with anything, and by the end of this lesson, you'll understand exactly why their stillness is their superpower, and you'll be able to compare all three group trends in one clear picture. Let's begin. 4 goals for today. First, explain why noble gases are so unreactive. Second, describe the boiling point trend down group 0. Third, link their properties to their real-world uses. And fourth, bring groups 1, 7, and 0 together and compare why their trends behave so differently. This is the session where the whole periodic table story clicks into place. So why are the noble gases so unreactive? It comes down to one beautiful fact. They already have full outer shells. Helium is full with 2 electrons, neon 2, 8, argon 2, 8, 8. And here's the crucial point. With a full outer shell, there's no easy electron to lose and no space to comfortably gain one. Reacting would cost energy the atom would rather not spend. So they stay single atoms, not even pairing up into molecules, and they simply keep to themselves. A full shell is a contented shell. Now a physical trend, and be careful, this one is not about reactivity. Boiling points increase down group 0. As we go down, the atoms get larger and hold more electrons. That larger electron cloud creates stronger temporary attractions between atoms, forces we call London dispersion forces. Stronger attractions mean it takes more energy to pull the atoms apart into a gas, so the boiling point rises. Remember, this is a physical trend about attraction between atoms, not a chemical reactivity trend. Here's where it gets wonderfully practical. Their properties give them jobs. Helium is low density and non-flammable, so it fills balloons and airships safely. Neon glows a brilliant orange red in an electric discharge, so it lights up advertising signs. And argon is unreactive, so it fills lamps and shields metals during welding. One tip that earns marks: always link the property to the job. Don't just say argon is used in lamps because it's a noble gas. Say argon is unreactive, so it does not react with the hot filament. Property, then purpose. Now let's zoom out and compare the 3 groups we've studied. Group 1, 1 outer electron, which the atom loses, and reactivity increases down the group. Group 7, 7 outer electrons, and the atom gains 1, and reactivity decreases down the group. Group 0, a full outer shell, no simple gain or loss, and very low reactivity all the way down. Look at groups 1 and 7 side by side. They trend in opposite directions, and now you know exactly why. One is losing an electron it already has. The other is trying to attract an electron from outside. Let's put the comparison into words, because this is the classic extended answer question. Why does group 1 reactivity increase, but group 7 decrease? For group 1, going down, the outer electron is farther away and more shielded, so it's easier to lose, meaning more reactive. For group 7, going down, an incoming electron is attracted less strongly, again, because of distance and shielding, so it's harder to gain, meaning less reactive. Same 2 ideas, distance and shielding, driving 2 opposite results. That's the elegance of chemistry. Let's check your understanding. Question 1. Why is argon used as a shielding gas in welding? Pause and answer. Because it's unreactive, so it doesn't react with the hot metal. Question 2. What happens to noble gas boiling points down the group? They increase because larger atoms have stronger temporary attractions. Here's your recap. Noble gases are unreactive because their outer shells are full. Their boiling points rise down the group as those temporary attractions strengthen. And comparing groups 1, 7, and 0 shows how electron structure quietly controls everything. You've just tied a whole topic together, and that's a real achievement. Keep that momentum going. Visit www.bridge2exam.com to practice these comparisons, test yourself with instant feedback, and work toward the final exam. Your future self will thank you. I'll see you next session where we start speaking chemistry's own language, symbols and formulae.